Hi everyone, can you guys hear me? Thank you. So as usual, we'll start around 11:10. So see you in 10 minutes. Okay. Hi, everyone again. Hope we had most of the people that want to attend this lecture live already here. So I'll start. And as usual, if you can turn on your camera, please do so. It helps me a lot. Okay, so let's start. So we're in week 12, as you know. And the first thing I want to do, talk today, is to talk about logistics, about next week's lecture, and about the exam. So I think you all seen the schedule, you know when the exam is. It is scheduled at 8 p.m., which is quite late. And I guess we don't want to delay things, so we want to start at 8. Right now, so I'll talk about the exam. Let's cover the next lecture first. Next week, we're going to wrap up, cover some general questions. There's not going to be any super heavy new content. I might have some interesting bits here and there for you as an opportunities on which courses you can take and things like that. And we can talk informally about that. And then we're going to do some exam review questions. Okay, so this is the plan for next week lecture. And we're going to have our last quiz this week. Next week, there is not going to be a quiz. Okay. Any questions about next week from anyone? There is a quiz this week. There is no quiz next week. This week, we still have a quiz. Okay. Okay. Any questions from anyone else? Okay. So let me talk a little bit about exam details. So exam, as you know, will be online. And for us, it will be take home in the sense it will be similar to what you had with your quiz, right? Where at certain time, everyone starts writing, right? And you would do it over Quarkus, right? We had a 33-hour slot dedicated, but I don't want to create a 3-hour exams to kill you. So because sometimes you start to make mistakes just because it's too long. So the exam is going to be roughly around 90 minutes. I didn't decide how precisely, but not more than 90 minutes. That's what you should expect. And I advise you to start right at 8, so you're still fresh and had more energy. So it's going to have multiple choice questions, similar to what you did with our quizzes already, but it will also have some questions. We're going to have a text box, and you have to type your answer in the text box. So this is usually for more complicated questions, but still not too long, so things can be reasonably typed in, right? So remember, we're going to ask you what should be there, and you need to provide the precise information. Also, there are going to be even more complicated questions where we would need you probably typing won't be as convenient. So what we advise is essentially write the answer and your logic on a piece of paper, and then make an image with your phone and then upload an image. Again, you wouldn't need to upload the whole exam because I've seen some people try to do this in the midterms and exams in their courses that create a mess and a huge load on Quarkus and things breaks. So here you're going to be periodically uploading individual, images for some questions, but for most questions you don't need to upload things. Any questions about that? So this is type of questions you're going to get. Any questions about exam, about what kind of questions you're going to get? Yeah, Corn, as someone said, has the exam time, and there's probably emails. I got an email about that, but you probably can see it in a Corn. I think it's December 12th, 13th. I need to check. It's at 8 p.m. Okay. Is it an open book? It is. So it's from 8 p.m. until 11 p.m. officially. So they reserve 3 hours, right? But in reality, you don't need 3 hours. Okay. As soon as you start, you're going to have like something around 90 minutes. And yes, it's an open book. So you can use your lecture materials, right? Approximately how many questions can we expect? That's a hard question, to be honest, to answer, Rakshit, because like each questions are different. So you're going to have multiple sections of the exam. There's going to be a lot of small questions that value less, and there's going to be a few big questions as well. So will the questions be, actually, so did I answer your question? So I don't know the precise answer yet. As soon as we build the exam, we know. It's like you've seen the quiz questions, you're going to have some of that small ones, but you had also get a bigger ones as well. So probably you're going to have, I don't know, 5, 6, 7 big problems and a lot of small ones. Will the questions be shown one by one, or it's all at one, or can we scroll? It's a good question. I believe it's probably going to be scrollable, right? So you can jump between the problems conveniently. But I need to test the Quercus myself to see. I would expect it should be somewhat similar to quiz. So you can go between different things. Okay. Okay, any questions about logistics? This part of the logistics. Is everything clear on that? So you've been through many exams, so it shouldn't be any significantly different, although there are some changes here because it's take home. Okay, and now if there's extra time to upload the images after the 90 minutes. So Winnie, so the goal is that essentially we want you to do it as you go, right? So I will try to time things so there's enough time to upload things, right? So you're gonna get some time in your exam engraved specifically for uploading, but I don't want to have, like, I've seen a very negative example where you upload everything at the end, because then the servers crash, because like when 100 people start to upload, load 20 pages of the exams, then when these things are overloaded. So what I recommend you strongly is to, as you finish the problem, then upload it, right? So it would be somewhat more distributed. Are there any supplement materials we are supposed to review, or just lecture slides are enough for final? So essentially everything you learn in the lecture slides and your tutorials, right? We're doing so because we can ask questions related to tutorials and what you built, in your, homeworks and projects. That can be covered in the exam. I'm not gonna ask anything that was not covered in the lectures. If there's any supplemental materials can be helpful, those are there. I provided the links to the textbooks, right? Those you can study if you want more generic information and you want to learn things a little bit better or go in depth. But again, as it was with the quizzes, right? I'm not gonna ask anything that was not covered in the lectures. So if you did study lectures, understand them well, then it should be enough. Are we allowed to write on tablet instead of paper? The answer is yes, whatever makes it more convenient for you. So the reason why I said writing on a paper is just I can't necessarily rely on everyone has a tablet or things like that. But essentially the point is entering some questions, typing would be too long. So like writing either on a tablet or on a paper is just faster. So at the end of the day, I just need to make sure that you upload a file in the format we can read. So it should be either PDF or JPEG. So we should be able to read it. So there shouldn't be a problem that, like, you use some weird format, say only runs on Mac, and if I don't have a Mac in my hands, I won't be able to run it, right? So just make sure it's stored in something easy to open like JPEG or PDF. Mohammed, does it answer your question? Yeah. So essentially, yes, if you study lecture and you did your homeworks on your own, that should be sufficient. You still want to revise, and on some topics I can go in more in depth, right? But overall, there won't be surprises. I've never heard anyone complaining so far and hope it's true that no student ever complained to me in person on Piazza that we asked something that was not covered in the lectures. So everything is covered in the lectures. Can we submit PDFs instead of images? I hope it is. We will sanity check before releasing exam to you. We will test it thoroughly. We'll try. I hope that Quarkus allows to upload PDFs, but I didn't test it myself, so we need to check. Right. Okay, so the hand, we will test it and we'll get back to you on the PDF question. I think it should be fine, but I don't want to lie to you about that. Usually if you have PDF, you can also convert it into JPEG, but it would be nice to avoid it. Yeah, we will sanity check, make sure that all common formats will work, and we would give you some clarifications on that. Okay, sounds good. Any other questions about the exam? And we'll have next week, we'll go about the exam again. I will show you some example questions. Any other questions? Okay, if there is no one question, there is still one thing that I had to go, which is not very, pleasant topic to talk, but I had to talk about it, is plagiarism. So essentially, I've been into many meetings and discussions of how to handle exams. And I'm going to tell you what I'm going to do. But before I tell you what I'm going to do, I want to explain you why we decide to do it. There are several strategies that professors are now during pandemic try to fight against potential plagiarism. One is I would call proactive, and another one strategy I would call reactive. So proactive strategy essentially constrains the way you write your exams. So they essentially force you to turn on your camera, stay from your computer. Sometimes TAs literally shows you the questions on the screen and you're not allowed to touch anything. So they essentially try to isolate you as much as you can. That's a proactive strategy. What I dislike about it is, first of all, it makes exams very uncomfortable for students that actually don't cheat, right, or don't try to copy paste anything. So it makes the environment very stressful, and things can break, the internet might not work, there can be all these different problems. So it makes things very stressful for everyone, just to fight a few people that want to cheat potentially, right? And at the end of the day, what's worse, it doesn't even guarantee you anything, because none of that is 100% secure, right? So you put a lot of pressure on everyone without a limited benefit. But you cannot completely ignore the problem does exist. So we don't want things being unfair for people to do it on their own versus people that not. So the way I'm gonna, and my TAs are gonna fight against it, we introduce a selective oral verification after the exam. So we assume that by default that you guys don't cheat, but if we see through the exam as the result that your answers is very similar to someone else, and you make like on a very complicated problem, you literally have everything the same. And if we are concerned, we can and we will optionally call this person out and would ask to explain how they solved that particular problem, right? So you won't know which problem we're going to ask you. We'll just tell you that we want to meet, and me and one of your TAs will go with you and say, please explain how you solve X, right? And if you did it yourself, that shouldn't be a problem, right? But if you didn't, and it's obvious you didn't, there would be a penalty, right? So this is, so it doesn't mean that we're not going to call everyone, but if there is something suspicious in your exams, right, then that's going to happen. So please make sure you write your exam on your own. It's anyway, we give you enough time. I'll make sure that you get enough time, and it's open book, right? You're writing it comfortably at home. We do not stress you and turn on cameras and like follow every move you do, but be also generous. So let not you like, we don't like to punish people, but if we obviously see there is a cheating going on, we're going to take actions. So any questions about that part? Yes, we are not gonna, if we clearly see that you did everything on your own, right? and there's no suspicion, we're not going to do an oral verification on everyone just for no reasons, right? It's going to only happen for the suspicious cases, right? But the penalty would be severe, so make sure to avoid that. So we're not going to just blindly say we believe you cheated because your answer is identical to someone else. Things might happen, but if we have a very serious concerns, right, for complicated problems, it's kind of obvious, right, when two people did like identically things. So what we're going to do, we're going to call out people individually, ask them to explain, and we'll try to figure out what's happened. And the final exam is on Quarkus. Yes, this is our plan right now to have it on Quarkus. So if there's a possibility that the internet might break halfway and are we allowed to enter in again? We'll test different possibilities, right? Yeah, so someone said you can rejoin them. Yes, so you should be able to rejoin and continue. So Glenn is asking, we will see all questions at once or one at a time. So I think someone asked that questions already. I think ideally, and that's my plan right now, is to make you able to see everything like all together. So we're not going to limit. So similar to if it would be in-person exams, we'll give you a printout and you jump over problems the way you like. We'll try to make things scrollable. So this is my plan right now. But again, my strong advice is for the questions where you need to upload something, like upload an image, don't wait until the very last minute, right? So upload as have you done with the problem. So that's an advice. Glenn, did I answer your question? And Jonathan, did I answer all your questions? Okay, any more questions? Yeah, you should be able to rejoin. We're going to try to test it with TAs as well. On quizzes, it was less of a concern. We'll test it. What I'm really worried if there's a total crash on Quarkus itself, because it happens previously, but this is nothing I can do at this moment about that problem. Anyway, at the end of the day, if it happens, you won't be penalized. You will be able to continue. We'll figure it out something, but yeah. In a general case, if it's just your connection, you should be able to rejoin. Yeah. Okay, so please make sure we don't need to talk about this last item of plagiarism with anyone. We really would prefer this not to be in a topic. So we'd make the exam reasonable. You all should be able to do it. We were, in general, if you look at their, your grades probably right now, you see we were generously marking everything. So do it yourself and you will be fine, okay? Okay, I hope I covered enough of that. So let's talk about technical stuff now. Any questions before I go and talk about today's week lecture? Okay, there are no questions. I'll go and talk about other stuff. Okay, so remember you were talking about function calls stack, push, and pop in the previous lecture. That was covered by Mustafa, and today I'm gonna talk about a really cool topic first called recursion, right? So this is something you always learn from, programming languages like C, but the question is obviously how you're gonna do something like that in an assembly. And this time I'm not gonna give you that as an answer, right? I'm gonna show you the possibilities and try to explain you why things are done a certain way and not the other way. So the easiest thing you can think about recursion is a factorial. We hope a lot of you are already familiar with factorial from your calculus classes. And essentially, this is a definition of the factorial in, in C-like language. So this is a recursion here. So how would you do recursion in assembly? Recursion is an interesting topic. I think people of you who watched the Inception movie could see some similarities. So, recursion is really tricky in a sense, is, to understand the recursion, you need to understand it first, which is kind of a recursive definition on its own, and that's how recursion works in general. So the question is, what recursion really is in hardware? It's one thing to write some code or mathematical recursion that has no constraints, but how would I go and implement it with assembly, right? That's an interesting question that we need to answer. Okay, so how would a regular recursion work in C, right? So when I call factorial 3, right, with an input 3, what's going to happen, I'm going to get P equals 3 multiply, and there is a recursion call here of factorial 2, where I don't have an output yet. So what's going to happen is I'm going to have another call of the function, right, factorial 2, and there I'm going to have 2 multiplied by factorial 1, and here's another recursion call, right, and then there is a factorial of 1, which is P equals 1 multiplied by factorial 0. Finally, factorial 0, we reach the base case of the recursion. That's always should happen for recursion to work. And factorial of 0 just returns as P equal 1 and returns. And then I return 1 here that goes back here, and I get 1 multiplied by 1, right? Right here in place. Then this thing returns P again, and this 1 multiplied by 1 comes here, and I get 2 multiplied by 1 in this function invocation. I get P equals 2, and that returns and come here. And here I get 3 multiplied by 2, and then P becomes 6. Okay, so this is the way how that static piece of code invoked into the real code. And the main problem for assembly here is that we need to know where explicitly store the values. So remember, when you use function calls in C, C creates you a nice abstraction, so they don't need to worry where the parameters are. You just write a function with a certain set of parameters, and whenever you do it, the compiler is responsible to figure out how to store these parameters, how to return them. It's not your headache. Your only headache is to write the function properly and have the proper parameters and signatures here and return the correct values. But that, manipulation and storing the values, the tedious process is done by you, by their compiler. But we need to store the values in the case of assembly, and those values that we need to store in assembly, there's no one to take care for us, so we need to do it ourselves manually. So what do we need to store precisely? We need to store the value of n. We also need to store the value of n minus 1. Why so? Because I need to pass this as a parameter to the factorial, right? So you need to store that somehow. And then I need to somehow to store the value of the factorial n minus 1. So I need this thing, right? I need this thing, and I need the result of this factorial. So those values I need to store somehow, somewhere, right? And then I need to store the return value. So it can be either 1 or that intermediate results, n multiplied by factorial of n minus 1, right? So those are return values that I need to compute and return somehow. So any questions so far? I'm not proposing you any solutions. I'm just saying what we need to do. And I understand some of you already got some experience with recursion, but some might not. So I want to make sure that all bases are covered. Questions? Okay. So design decision number 1, potential. So if I want to store values, what's the first obvious choice? Well, the assembly so far, and when we write a lot of functions, we store everything in registers, right? So one thing you can suggest is, well, let's keep the values in registers. So for example, we can store n in the register T0, n minus 1 in register T1, then we store factorial n minus 1 in T2 and return value in T3. Would this work? So anyone sees any problems with that proposal? Please type in the chat. Yeah, so as Jonathan said, that quickly becomes a problem. It doesn't work. Why it won't work? Well, you're going to store n equals 3 in T0, right? And then it's not even the fact that it's not enough. The thing is, like, you're going to get a conflict. So in the next call, you're going to store n20 in T0. And what's going to happen is going to be overwritten. So you can try to play a smarter games around it, but there are two problems. First, there is conflicts. You're going to do, if you're going to store in registers and use the register philosophy, you're not going to be able to track which instance you are, and your register will conflict, right? And they will be overwritten and essentially lost. Or if you do something smarter about using T0 first and then T1 next, you will be get out of registers. So this is problem for all registers. So you cannot do the naive thing, right? Then essentially, fundamentally what happens, register is like a laundry basket. You put your stuff there, but when you call another function, or a person in our case, that person will use the same basket and mess up your stuff, right? So essentially, there is no protection of the register from someone's calling. And why the mess happens? The mess happens definitely in this case, not by chance, because that other person is you yourself, because it's a recursion. So you're gonna call yourself and you're gonna mess up your own stuff because you use registers the same way. So essentially, this is more like, you know, in matrix, where you just get a lot of clones of the functions with slight variations, and it's still your own function, just called multiple times. So obviously, the correct design decision here to use is, and you know the answer by now. So hopefully someone will type it. Yes, thanks, Sam, and others, Shu and Christina. So it's stack, right? We had to use stack. And not because we like to use stack, we really have no choice, right? The stack is there for that reason. So essentially, the way to think about it is that you get a stacking laundry baskets for, you know, for efficient representation of things. And essentially, for n equals 3, we use the bottom. For n equals 2, we use the middle one. And each recursive call has its own dedicated space for storing the values, right? And that's the key. So each call, when it's running actively on the hardware, it has its own working space. And if it's that call respects certain behavior of correct operation with the stack, things are safe. So what are the useful things we need to know stack? First of all, the stack has a lot of space compared to register. The question for you, why is stack has so much space? Why I don't have that many registers, but I had a lot of space for stack? How is it possible? So this question requires some thinking, but you learn everything on this course to answer this already. So why I have only a few registers and those are limited and numbered, but for stack I had a lot of space. Yes, thanks, Sam. Exactly. Stack uses memory. Remember, registers are, you know, we'll learn about how they're built, right? They are actually, you know, SRAM storage that's very limited and very expensive to build. It's much faster though. So it's stack essentially has a lot of space, but the stack, you know, back up by memory. So Krutik make a comment, it's pointers to cache. I don't understand what you mean exactly by pointers to the cache, but one thing is that fundamentally stack points to memory, but if it's a frequently used part, right, it's not going to go all the way to memory, to the real DRAM memory, where it's going to go to something we learn, which is cache. So instead of going and spending 100 cycles to read every parameter from the stack, we actually might be sitting in L1 data cache, and that might be something like 4 cycles, right? And 4 cycles versus 1 cycle of register, or 2 cycles of register would be, you know, comparable. But fundamentally, the reason why it's so large is because it's backed up by large memory. So it might be somewhat slower, but it has a lot of space. Any question about that? Does everyone understand why this happens? So there's a trade-off here. You get more space, but it potentially somewhat slower. Okay. The way we manipulate the stack is last in, first out order, right? So it's suitable for implementing recursion and function calls. That's why we use the stack here, not the queue, for example. And that's how the stack operates. So, so essentially the way it would work, we do n equals 2, right? Then we do n equals 1, and then n equals 0, right? Notice that everybody is getting the correct basket because of last in, first out, right? So we now made our design decisions. It's time to actually start writing step by step a little bit of assembly code. So let's look at this piece of code, right? Essentially, that's what we're gonna do. So the first call is for n equals 2. And we need to, obviously, to return correctly, we need to store return address, right? If I call something, there's no like real function call, as you remember in assembly. So if I go somewhere, it's only jump. So if I jump somewhere, I better be knowing how to jump back to return to the old place. So I always need to store the return addresses. Then I store the return address, then I get n equals 1, then I go through A1, so I store another return address, then n equals 0, then another return address, and then I reach the top, the base case, right? And then I start to unroll things and go backwards from my, queue. So I get P0 equals 1, right? So P0 is a return value here. And then as I unroll things through my stack, then I'm gonna go into P0 equals 1 in this factorial one after I finish with this call, right? I go into this thing, and then I had my return A1 here and N1, and that's P0 I got already from, returning the base case. And then in this calculation, I'll get P1 equals 1. I put it back on the stack, and then I get another call. So I got all the way to the top here, and there I had a P1 equals 1. I had my return address here, and n equals 2. So I'm gonna do my math. I will get P2 equals 2, store it back on the stack, and then we're done with calling it. Right? This is for factorial n equals 2. Okay. So so what that flow dictates us. So there are some tedious steps we need to follow, and they're important, but not fundamentally difficult. So let's look at those. So there are a few things we need to do before making a call and finishing the call. That's what we do. So before making the recursive call, we pop the argument of the stack, pop argument n. And then we push argument n minus 1 and minus 1. Why do we do so? Because that's an argument to be used in the recursive call. So we need to give the next invocation of the same functions the right argument on its stack, n minus 1. Then we also need to push the return address, the current return address, because we need to remember where to return when we're done with the recursive call. And then we make the recursive call itself. So, and when I make the recursive call, I mean, that's there, the jump that we do. After finishing the recursive call, what do we do is no surprise as well. We do everything in the reverse order. So we pop the return value from the recursive call. That's the value we need to know. And then we pop the return address, right? Because that's the one that was stored in the stack. Why are we doing this order? Because remember, the return address we pushed ourselves. The inner function, when it worked, it did some math on the stack, but eventually the only thing we expect from it is it puts its return value on the stack. And that's why we pop it here. Then we pop our return address because that's what we put ourselves, right? And then we compute return value. That's what we do in the main body of the functions. And then we push the return value. So the upper call can get it. So that push is what we're reading here from a previous version. And then we jump to the return address we're supposed to jump, right, to the return one. Well, everything needs, see how everything needs to be in sync, right? So if you change the order of things, you need to make sure you don't read something incorrect. So the thing here is that you can easily change it, because if you just say, let's, if you change these things, because remember, the first thing you really need to do is to pop the return value from the recursive call, right? And you might probably change, like, I don't think you can even easily change things, because if you push the return address last, you need to pop it here, right? So anything that manipulate here, you can get it in another way, but then you would need to more pushes and yeah. So I had another question from Yujan. This only works when we don't need n to compute return value, right? Since if I need n, then I need to keep n in stack before calling recursive. That's a good question. So right now I try to keep it simple. So in reality, this push here, it cannot be not just one value. So if the recursive function has many parameters, I need to push each of these parameters here. So that push, think about it, there can be a loop here. For each parameter I want to have, I need multiple pushes. And then I push the return address at the end. And that's one of the reasons. So Yujan, did I answer your question? So if you need more parameters, you will need to push more values. You mean about pop argument and? So what's the question about pop and? Because I think your question was about pushing. Well, and for the current call doesn't need to be pushed because it's not used in computation. So essentially, as you wrote it, why do we pop it when we need to later to calculate? Well, we pop it because I'm a recursive function. So this is my argument, right? I don't know what my n is, right? So the first thing I do, I pop my current n, right? Because when I call factorial n, that n does not exist. I don't know what my n is. I don't know I'm factorial 3 or factorial 2 or factorial 1 or factorial 100. So the only thing I know, I'm factorial. And the first thing I do is say, like, which factorial I am. So I pop the argument from the stacks. It tells me which factorial I am. Yujan, does it answer your question? So you need to take you need to get your n first. And then you know that whoever you call it, you take that -1 and that you pass into the recursive call. Yujan, did I answer your question? Yeah, so it's like the problem is like when you had factorial, except for the first case, you don't know which parameter you were called with. So at the beginning, you know, I'm in factorial. I need to know which parameter to operate with. So the way I know, I read something from the stack to know what I do. And let me return back to the question that Zihao asked here. So she said, can we change the order of push and pop, like first push return address? And the answer why it's problematic is here you had push and you push one argument. What you to have 10 arguments here. Then when I come back here, right, it might be actually quite, in the actual function, it might be non-trivial to know where the return address has to be versus where the arguments are. You need to know how many arguments you have. That complicates things a little bit. So you know that the first thing you get is the return value, right? Because there's only one of it. And then you get the return address because there's only one of it, right? And that makes things much simpler. Yeah. Okay, so let's move on. So let's start to do some mapping of the code. So as I said, we need to pop n of the stack, which is essentially storing at T0. And then you check if T0 equals to 0. And we're going to put our n in T0 and 1 in T1 and factorial n -1 into T2, right? And then if t equals 0, what we're semantically doing, we push return value 1 onto the stack and return to calling program, right? Return to where we're called. If t0 is not equals to 0, it means we're in the recursive branch. We push t0 an array onto the stack, calculate n-1, push n-1 onto the stack, and call factorial. After some time, where that thing call returns back, then we do the pop of the results of the n-1 and store it in t2, right? That's what we do. Then restore array and t0 from stack and multiply factorial n-1 and n, right? And push result on the stack. So if somebody asks you, where's actually factorial actually computed? So it's not computed in one place. At each particular place, what you do, you take two numbers and an n-1, multiply and pass it to the next layer, where it takes these results and multiply it with n+1, essentially, right? And so then you push result into the stack and return calling program. Okay, let's look at how the assembly gonna look like. I try to go over it, but I cannot cover every little detail here. And remember, the code on the slides are not guaranteed to be correct. You need to be able to find some errors and fix them. So there might be some typos here and there. But hopefully the general idea is clear. So, so the first thing you do, pop n of the stack, right? So that's what you do. And essentially then you had, two cases. This is your base case, right? This is where you just, happen to be 0, right? And then it's you're done, right? You add 0 with 1 and put it back onto the stack. Why we use branch not equal instead of branch not equal 0? Well, so essentially if we found that, I don't think it's a big difference here. So the only thing you need to check whether that's, 0 or not, right? So because you're checking with 0, so it doesn't really make a difference. Okay, so then this is the base case, right, when there's no recursion, and there is the case with the recursion, right, where we manipulate the stack, shift things properly, right, push t0 and array onto the stack, right? So this is t0 on the stack, this is array into the stack, right? And then we prepare the right, address, and then we jump to the factorial again, right? That's the call for the factorial. So this is up to this point we cover. Someone says, could you have done this manipulation with stack and stack? And the short answer is yes. The compiler will eventually optimize this code dramatically. Right now, I'm showing the simplest version of it, so you don't would be not confused with this, because if you optimize it, there's a lot of things will move here, right? Yeah, but essentially the way things work in the compiler is going to take the C code and then it literally going to do each instruction by instruction. And then it's going to look for opportunities to optimize, and it's going to see there's 3 instructions doing the same thing. So you could just shift it all together. Okay. I mean, did I answer your question? So essentially, if you're going to run compiler with O0, you're going to see things similar to what you see here. If you're going to run it with O1 or 2 or 3 level of optimization, that will be optimized. And a lot of other things will be optimized as well. Okay, and then we go to the latter part where essentially we're done with calling the factorial. What we do is the follow-up, right? What we do is we pop the results of the factorial n-1 from the stack stored in T2. So this is our load. Move the stack +4, load array, load T0, right? Move the stack accordingly, and do multiplications. That's the only instruction that really computes, right? Yeah. Okay. So Sam is saying, but would you have to do, yes, you would have essentially, if you do, you guys want to do optimization, so let's talk about it. I want to first everyone understand the basics, but the short answer, yes, you like you can load, like if you don't want to do this 3 times, right? You would do it once, and here you're gonna use load 0, load 4, and load 8 as Sam wrote. So you would have why that's better, because that small addition here engraved in instructions, you're not spending an extra instruction on that. Okay, but that's an optimization. Semantically, this is what's going on, instruction by instruction. Any questions here? And then this is really the one thing where multiplication happens, right? And then we get the bits needed for multiplications, and then we store the results onto the stack. Any questions, guys? Okay. So that was as simple as it can be for recursion, right? Essentially, there are some rules that we need to follow for things to work. So before recursive call, we store the register values that you use onto the stack, and then you restore them when you come back to that point. And you store array as one of those values to remember where each recursive call should return. So at the very minimum, you should deal at least with array, right? At least with one thing. And so if you go and translate it into the actual assembly, that's what it's going to look like. This is, your main function. This is the factorial. This is the first time when the factorial is called, like factorial 10, for example. And that is the code for the factorial, right? And that's what's there, would be generated by the compiler. And this is essentially the second part. And you see it's very similar to what we look. Okay. Okay, so the bottom line of what we did here is that you need to understand that assembly magically doesn't support recursion as higher, more advanced languages that more high-level languages that you used to work with, right? And assembly is just a linear sequence of instructions that have ability to branch. So everything you want from a recursion to work, you have to implement using these linear instructions plus branches, where you jump to the beginning of the program over and over again. So that's essentially what you can do. Essentially, everything that assembly can do is looping, right, with branches. So the way, if you say how we were able to do recursion, is really due to the stack organization. So we were following certain principles on how we put things on stack and remove things on stack. That would allow us to model essentially the function calls, right? And not surprisingly, that's essentially what the C compiler is doing for you. So whenever you write in a C code, there is no miracle. Someone takes your function call and transfers it in the compiler, generates the code to manipulate all the stack pointers, and your recursion eventually mapped to this assembly language, and there's no real recursion there. Everything looks like assembly and manipulation with the stack. So how would it gonna look like, right, from the stack perspective? So essentially there is initial call to factorial, and you had x equals 10 onto the stack. And as you call more and more, at some point your stack keeps growing. So after third call, you're gonna have x10, return address number 1 onto the stack, then x9, another array to x8, another array, and then x7. That's what you're gonna have on the stack, right? That's what your stack is gonna have. And then after you fully unroll the essentially the factorial call, what you're gonna essentially have is this stack, right? So it's gonna be very long up to the way x equals 0. And this is where we finally reaches the, 1 on the stack, right? And we got to return 1. And then we get this long stack here, and we start to unroll it back, and we do it step by step, calling back until we get return 10 factorial at the top level of the recursion. So your stack grows and then it goes down, right? So this is the way it works. So you can recurse for some time, but the stack is not infinite in size. So there is always a limit on the number of recursive calls. So mathematically, your recursion can be infinite, right? But there's no infinite in real hardware. So the stack would be eventually out of space. And when you exceed this limit, you get a stack overflow, one of the exceptions that you can generate. And all content of the stacks will be dumped, right, to you, and you can investigate the problem. So essentially, if you write a code, and in your Python you get endless recursion or too deep of a recursion factorial you can't compute, and you'll get eventually out of memory. Okay, and that's the overflow you get. Okay, so I think we are slightly already at 12. So any questions so far before we go for a short break? Yeah, I forgot to ask Sam. I hope I answered your question well, right? Do you have any follow-up on your question? Okay, if there are any other questions. How do we find the stack size limit? This is something parameterized in the operating systems. So usually, just to be honest, you shouldn't write the code that really exceeds that. Like if you just try with factorial and give it too large of a number, you're going to see this very quickly. Like if you give it like a huge number, you're going to get overflow. But before that, you're going to start to get numerical overflows because the output is too large, right? Because like as you multiply numbers, they keep growing. There are a lot of different functions, like Ackermann functions, for example, you can play with. But the stack size limit is fundamentally limited at least by the capacity of the memory, right? Things would be very slow if you don't fit into the memory. So there is a certain space dedicated by the operating systems for your stack, right? And if you get out of that, it becomes unreasonably slow, so it just generates you an exception. So you're not supposed to know it. Most reasonable implementation should never reach that limit, right? You shouldn't get millions of values on the stack normally. You're going to learn more in theory. You would learn that a lot of recursions functions can be rewritten in the loop representation. So in general, recursion really exists more for convenience, right? So there are, pretty much anything can be rewritten without recursion, but that might have much less elegant implementation. So for some simple cases, recursion is just better. So if you use it properly, the recursion is just a nice way to implement things, but you can always do things without recursion. Okay, so any other questions? Okay, if we don't have questions, let's have a short break until 12:10. So I see you in 7 minutes. Okay, I hope everyone is back, so let's continue. We talk about the specific example with how we implement recursion for factorial. Let's make it a little bit more systematic. So everything we did so far was really ad hoc, to be honest. We stored an argument on the stacks, we say the array registers, but how do you support recursion in general? So essentially, the way it's done, and I already hinted about how that would be done by their compiler, for example, you must know the signature of the functions you're calling. So you had a function call, like a function signature, you know all the parameters. So the number of arguments is key so that you know how many things to pop from the stack. This is why C has so-called function prototypes, because without that, it's very difficult to follow the stack culture. So you need to store the values of all the registers that you use onto the stack to operate. There is one optimization that you can do. So to reduce the number of registers that needs to be saved, MIPS and other, architectures use caller save and callee save registers. There's a question here. Is there any languages without function prototypes? There are languages that they hide this complexity from you, but in reality, there's no free lunch. So if that's the case, if you have, there are such things as functions with, with dynamic number of parameters, right? But this is all quite expensive. In reality, someone has to still implement it. So someone's gonna implement something complicated with the memory and stack where it would dynamically allocate memory for you and move parameters in and out, right? So the languages might exist and do it, but that's usually more expensive to support it. Even in C, there is a way to dynamically show, there is a way to say that after that there's follows, variable number of parameters, right? Okay, so what's the optimizations about caller and callee is? So we had certain number of registers. If we have to be conservative and know that any single register can be changed anywhere, it means that all the time I will need to push and pop all the registers. So that kind of complicates things. So to avoid that, there is certain convention that was proposed. And essentially the idea is that that's what MIPS does. So there are T registers that are caller save. So if you're using them and want to keep the value, save it before calling the function. So essentially the T temporary registers are for current manipulation, right, within the functions. And you don't need to, to manipulate them. You don't need to push the old values on the stack and then restore them. That's for you to save to manipulate. And there are S registers, right, that are callee save. If you want to use them, you should save the values before using them, right? So essentially, this allows to differentiate which registers I can manipulate easily without pushing and popping the stack, because that's going to memory, that's expensive. So you prefer to go to use registers. And so the questions to you, what advantage do the schemes have over the baseline where would I need to do everything, push and pop? In the general case. Do you guys see the advantage of this convention? So anyone? I think I already hinted on the answers here. So Calvin, if you're gonna start saving the return value in the register, remember I showed that, is there might be some complications because you can use a particular register as a stack, right? So you can push and pop the particular register, right? through the saved registers, yes. But it's essentially would still be complicated, I believe, because if you would do this, then you would always need to restore it and make sure that's not properly overwritten. So there you anyway need the stack. So why not just keeping everything on the stack to begin with? So the real reasons to break out into T and S registers is to make sure that whatever compute you need to do, you can do most of it with T registers, right? And you don't need to push and pop them from the stack to do the manipulation. That means you don't get this ugly code where at the beginning of each functions, the first thing you do, you just pop a lot and then push a lot at the end, right? So you just manipulate with T0, T1, and others, right? So why are the registers are not even written in this scheme? Amazing questions. Anyone wants to try to answer that? Okay, no one? Okay, then I'm trying to answer. So the safety comes from the convention. So in reality, right, most of the code and the assembly code is generated. So essentially the convention in MIPS says that it's okay to not to save these registers, and means most programs could assume that's not done. If someone's like you decide to break this convention, that you might get into trouble. So that essentially becomes your problem, right? So essentially there is a convention that helps these optimizations, and it's not guaranteed by hardware in any way. This is just to simplify your lives and the people to write compilers to save time on not pushing and popping unneeded stuff, right? So instead of that, there's separation. It's usually not registers for everyone, and the registers even has the proper names, right? So usually the compiler won't generate the code that would disobey this convention, but you can ignore it and then you will be in the trouble. But essentially, to say why really it's not, is just because that essentially it's an informal rule that you better be following or you might be in trouble. But in hardware, there's nothing that really controls that. So you can violate them and, override the registers if you want. Okay, but that's a very convenient optimization that people agree on and follow. Again, as I said, most code in assembly code is generated, so it's relatively easy. The compiler never generates the code that would ignore these rules. Okay, so we finished with recursion. Any questions here? So I talk about the general recursion, show you some optimization so you can see how things might work. Okay. Now we're going to talk about another interesting topic, is interrupts and exceptions. So what are those things as interrupts? So interrupts is essentially the events that take place as an external event and requires a change in execution. So what are the typical examples of interrupts and why they're needed? So you might have an arithmetic overflow or a system call, or someone press Control-C on your keyboard, or you get an undefined instructions that you don't know what to do, right? So those are usually signaled by an external input wire, which is checked at the end of each instruction. So essentially, you can think about it. There is some magic bits in your hardware dedicated for those exceptions. And if one of those bits are set, then essentially you might need to go and redirect the control flow somewhere else. Because if you, for example, multiply two values and there is like an overflow and underflow, right, it might be not acceptable. You actually handle it, right? So essentially, those are high priority and they usually override other actions. So instead of continuing your regular code, you actually want to go and handle those interrupts, right, first, then return back. So what you need to think, like you can think about it as you need to go jump somewhere else, do something, and then return back, because that is so critical you cannot continue, right? So interrupts, as you can imagine, are quite fundamental. So it's like, if we wouldn't have an interrupt, we wouldn't be able to operate properly because, for example, when I press the keyboard, that's an interrupt, right? I need to stop what my computer is executing and react to my keyboard, right? And do something to it. So a lot of events and, the way we talk to the machine and force the machine to do something else is all built on the interrupts concept, right? That breaks the current flow and goes to another flow. Okay, there are two ways of handling interrupts, general ways. One is called pole handling. So essentially the processor branches to the address of interrupt handling code. And this is called interruption handler, which begins a sequence of instructions that check the cause of the exceptions. They might need to figure out what the type of exception was, and then they do some, follow up and some fixes and return things back. This is what MIPS uses. So essentially it's a syscall and that it checks the special V0 register and so on. And another option is so-called vector handling. The processor can branch to a different address of each type of exception. Each exception address is separated by only one word, and the jump instruction is placed at each of these addresses of the handler code for that exception. So there's no need to ask around. So essentially, you can think about it, there is like a vector where all the exceptions are written, then numbers, like number 6, 7, 8, blah, blah, blah. And then when I jump there, from there, I jump to some other place. Because I jump to location I know, when I jump from that location, I know precisely which exception I'm handling right now. So there's no need to ask around for the type of exception. So interrupt handling. So essentially in the case of pole interrupt handling that the MIPS uses, the processor jumps to the exception handler code based on the value in the cause register. And essentially that register has the written predefined parameters for different exceptions. So there is like some generic interrupt, there is address violation, address error exceptions on loads or stores, the bus error, as you can see here, there is like fetching data issues, syscalls, breakpoint that you can say put when you use say debugger, there's a breakpoint thing, the arithmetic overflow and some others. If the original program can resume afterwards, this interrupt handler returns to program by calling RFE instruction. Otherwise, the stack contents are dumped and execution will continue elsewhere. So for example, when you get your sec fault, right, that's essentially one example. What is gonna happen is it's gonna load, for example, something that is like a non-address in the memory or an incorrect address or protected address. And that's gonna just dumped, or like you try to load from null, right? Like what's gonna happen is essentially you're gonna get a dump and you're gonna get a segmentation fault, right, error, right? And and the above happens in their essentially kernel mode, right? So those are the interrupts. So the exception handler is not a miracle thing. It's just some, assembly code, just like any other function. But there is something unique about it. And the unique thing, it's not allowed to have another interrupt. So it cannot cause any error. So there is no one to handle it. That's a problem. So essentially, what happens is that whenever there's an event happens or when I press a button, when this code of an assembly works, any other event at the time is going to be ignored. I'm in a special mode where I need to be very fast, that I need to handle that event or error, and nothing else can break me at this point. So there is no option to have any overflow or anything. So this code has to be written so there's no exceptions possible at this moment. Any other exceptions will be kind of ignored at this time. One particularly useful error handlers in the old days used to be the one that take 80% of the OS code, and those error handlers were like humongous. So the most of the code you're gonna look like in the old OSs was all error handling, and they all had their specific handling like optimized for this case. People quickly realize that becomes really annoying, and they start to unify things in one particular way. And essentially there's some general ways. Essentially, if you have something you don't know how to handle, you get a kernel panic event and you dump information and ask human to reboot the computer. That's, you know, the general solution if you had some critical event, okay? But there are a lot of other interrupts that are handled normally, like the keyboard presses, okay? Any questions about interrupts? So this is not something you deal too much in this course, but you need to know about their existence and you need to know what they are and how they're handled. Okay, so now let's talk a little bit about things you're going to learn in the future courses, and that's important on their performance, not just the functional correctness of the operation, which is parallelism. So the key idea behind parallelism is that you can derive benefit from completing multiple tasks simultaneously. And parallelism is all about performance. And when we discuss performance, it's important to define the metrics on which we measure the performance, because it can be power, latency, throughput, you know, capacity, cost, anything can be a metric. It can be, you know, performance per dollar, anything can be a metric for performance. So the two metrics we're going to talk a little bit today is latency and throughput. So the latency is literally the length of time required to perform an operation. No surprises here. So in the real world, it's something like how long it takes to travel from point A to point B on Highway 401. And essentially, this is something where we use different forms of timing analysis and try to, you know, optimize the latency. Why latency matters? Well, for example, if I travel somewhere and I need to get from point A to point B, that's the metric I care about, right? I care about how long it's going to take me to get there. But that's not the only metric. And throughput is another important metric. That's the number of operations that can be completed within a unit of time. So how is it different from latency? So if you go back to the highway examples, it's how many cars arrive at B from A via Highway 401 per hour. So you can ask, why do I care how many cars care? Well, you might not care, so your metric can be latency, but the city cares about the throughput of the highway, so they care somewhat less about how quickly you get from A to B, but they care about how many cars would go through it on average. And obviously things are not completely independent. So you had terrible latency for everyone, then throughput is going to be low as well, but they are not interchanged, right? So for example, if you ended up have a broken car, or, you know, and your latency was poor, but the overall throughput is still good, that's what the city cares about, right? So if everyone's latency is poor, then throughput is also poor. So the metrics are not completely independent, they're related. But the throughput is more about multiple tasks, and the parallelism by latency is more about, you know, end-to-end performance, like for an individual task. So latency is about how fast an individual task runs, and throughput is about how multiple tasks run together in parallel. So one good examples of thinking about throughput is about your graphics card versus GPU. So the graphic cards doesn't process each pixel sequentially, one by one. That's very inefficient. Your fancy GPU cards typically process all the pixels in parallel on the whole frame, right? And they do the same thing. This is why the special hardware is built to optimize for throughput. Any questions on that? Those are important metrics to understand. Anyone have any questions? Okay. What are the type of parallelism that exists in hardware? And please don't confuse this with locality, right? That's parallelism in hardware rather than the memory locality. That was about storing data. This is about computing. So there are also two types that had confusing name with locality, but please be careful and don't mess them up. There is a spatial, essentially parallelism, which is when you complete the same task multiple times at the same time. And there is a temporal, also called pipeline parallelism, that breaking tasks into small pieces so that multiple different instructions can be in process at the same time. So that might sound confusing. Let me show examples. So this is an example of a spatial parallelism. So you had the same task done for many inputs, right? That's the thing, completing the same task at the same time, just on different inputs, right? That's spatial parallelism, right? This is what, you know, GPUs are doing, right? They do a lot of similar instructions on different data. Okay, that's spatial parallelism. And this thing is temporal or pipeline parallelism. So essentially there's one task, this task is broken into small pieces, and then we try, you know, each of the unit just does one simple task, right? So what's the difference between, you know, spatial and temporal parallelism? So essentially the way you can think about it is if you think about, you know, I don't know, cooking, for example, and you had multiple trays, right? So you had Ben and Alyssa, right, cooking. And the way you would do, there is a latency and throughput. So let's look at the timeline here. So everyone is still with me. I guess can follow up. Can someone confirm you're still with me? Okay, thanks. So let's look at spatial parallelism here. So the way it's done is that you had two actors, two compute units in a way, Ben and Alyssa, and there are two subtasks that involve into cooking, roll and bake, right? And roll takes that long, 5 milliseconds, and bake takes 15 milliseconds. The way you would get it with spatial parallelism, if you're gonna do both of these compute guys to work in parallel. So they're both gonna handle tray one. One is going to be handle tray one, another one is going to handle tray two. When they're done in 20 milliseconds, they will switch to another tray, right? And they're going to do this and this. And overall, in 40 milliseconds, they're going to handle 4 trays, right? And that's kind of, you can think about the throughput here. So this is the latency, 20 milliseconds. And the throughput, you can just say how many, you know, if you take the time, like a 1 minute, you can say how many trays you were able to handle in, you know, in unit of time, okay? And you can see this, for example, here in 40 milliseconds, I was able to handle 4 trays. Temporal parallelism is different. It's about a single task. So instead of doing this and this sequentially, you try to do things in parallel. So how does that work? So essentially, Ben rolls one thing, right? Then on tray one, it puts it on in the baking mode. Well, this is baking, right? Ben is not really busy, so he can start to do, you know, the roll on another tray, right? Then when the baking is done, and assuming you only had one compute unit, so you can only bake one at a time, right? When that's done, you essentially already have a possibility to start, you know, baking the second one because it was already rolled. So what you're gonna see is that this guy is gonna be done early than in this case. So as you can see here, because that was parallelized, so the tray 2 compared to tray 3 that was Ben was processing, was here the latency was 40 milliseconds, right? Because it done tray 1 and then tray 3. But if you look at tray 2 here, that was happened in 32 milliseconds because piece of the computation was overlapped. So this is essentially two types of parallelism. This is about how to parallelize across multiple compute units. This is how to pipeline the process within one compute unit to make it more efficient. Okay, so while something else is going, don't waste time and do something sequentially. Okay, so any questions about this cookie kitchen example? So Sam is asking, why is the roll band 3? So you're essentially saying in temporal, why I wouldn't do this thing here? I guess there, So there is some assumptions on how much you can do, right? How many trades you can actively run, right? So that's kind of the assumption there, because there's a single compute unit. But you're right. So then if there would be no dependency and complications, you can imagine that Ben was keep rolling out, rolling multiple things while cooking, right? But then if you're gonna do like 3 here, then at some point you would be still bottlenecked by this guy, right? So there is nothing that you would have to do here. So you cannot roll an infinite number of cookies in advance, right? So if you know that you eventually bottleneck, you just overlap on the one, because it's not beneficial to overlap anymore. So essentially, is it possible to have both special and temporal at the same time? Yes, exactly. So if you're gonna go and take more advanced courses, you're gonna actually see this. But let me finish with Sam's question. So Sam, did you answer the reasons why it might not be beneficial to do multiple? So if you had an infinite resources, right, you could keep rolling more in parallel to that. But if eventually you're out of some resource, there's no extra benefit, right? Because you still need to bake, and bake is sequential, so there's no benefit to overlap more. Because I need to stay tuned, right? Because if I essentially rolled 100 in advance and then my bake still there, there's no benefit, right? My critical latency is still this. You see it, right? Yeah. So in reality, you try to balance out different things. You try to making sure the things are parallel, but here there's just no benefit. So essentially, if you were banned, there is no advantage to keep rolling too much in advance, right? But at the same time, you don't want completely waste time where you're baking. You want to do at least one, roll while doing that, and that cuts the latency. And then coming back to Rakshit's question, spatial and temporal at the same time, that's exactly what GPU is doing. They're essentially gonna have a very simple pipeline mechanism, 5-stage pipeline that I'm gonna show you today. It's also using very old days CPUs, but it also had a lot of spatial parallelism. So you try to get the best of both worlds, both parallelism. Okay, did I answer your question, Rakshit? Okay. Okay, I'll show you an example of pipeline microarchitectures. Essentially, how does that work? So essentially, remember how we execute a program. We first load the program into memory. And then we set the program counter for the first instruction in memory and set the stack pointer to the first empty space on the stack. Then we let instruction fetch, decode, and do the work. And the processor can control what instruction is executed next. And when the process needs support from the operating system, it will put a trap or throw an exception. So essentially, those are the stages of the pipeline, of the simplest possible pipeline you can imagine. That's called usually 5-stage pipeline. If you would be an engineering department, they would typically ask you to implement this 5-stage pipeline in Verilog or something like that. That's a typical assignment the students do, so to feel how the typical pipeline processor works. So essentially, there are 5 stages. There's a fetch that updates the PC and locates the instructions to execute. There is decode that translates the instruction and read inputs from the registers and register file. Then there is an execute address computation using the LU. That's where the real execution happens. And then memory read or write. Memory operation that must access memory. And non-memory operation can skip this part. And there's a register write back, then the result is written. As you can imagine, we try to pipeline those things as much as we can. And essentially, this is the example of the timeline, somewhat similar. It's very oversimplified, but it gives you a feeling the difference between pipelining with or without pipelining. So essentially what happens is without pipelining, if I do 5 stages, and then I do another 5 stages, with some realistic latency, that becomes 950 picoseconds. That's my latency. Throughput, though, and the latency is as fast as it can be because you can't really go any faster. But the throughput is 1 instructions per 900 picoseconds. So that's roughly 1 billion instructions per second, right? So like something like 1 close to 1 gigahertz type of operation. How about pipelining? So what we're gonna do, we try to pipeline things when we can. That goes back to Sam's questions, what can be parallelized, what's not. There are more stages here, there are more things, tricks we can play. essentially there's a first fetch instruction, right, as we go, and then we start the decoding, right? And in parallel with the decoding, we can start already fetch the next instruction. There's no reason not to. So we do decoding, like we read register, and then we execute in the LU, and that can be overlapped with the decoding here, and that's overlap also with the fetch of the next instruction. And this is a memory that can be overlapped with the execution stage, and this is a write register, right? They all fixed length. So we try to organize this pipeline that it gets a nice steady state. So what's the point we can see here? What we can see is because of the alignment issues, and we want to things put, more efficient and being proper, like we get some little bubbles here of misalignment. Because of that, the latency becomes, we try, so essentially we bottleneck by the latency of the longest stage, right, in a steady state. So the latency of the fetch is the longest here, or memory is the same, I guess. But overall, you gotta get a latency of 5 by 250 if you want to do 5-stage parallelism, right? And that the latency becomes 1,250 picoseconds. So, and this is, as you can see, is worse than here. So it's a valid question, is why would we do this? What's the benefit? And this is the benefit. The benefit is that on average, we now can handle one instructions for every 250 picoseconds, right? Because that's essentially what we can do in the steady states. We on average do one, right? Because of the parallelism, right? I'll see how I'll get back to your question. So the throughput becomes 4 billion instead of 1 billion. So I improve my throughput by 4x by sacrificing some of the latency. So let me come back to the how questions and ask why this latency is this much. So remember, you have small pieces and large pieces here. Things are not equal. When I'm going to be doing a pipeline, if you ever been to a factory, they try to make each stages as close as possible, but there are still some stages are slower than others. So to synchronize things nicely, if you start to pipeline things, at every stage, you cannot do fetch faster than 250 picoseconds. So essentially each stage of the pipeline, if you keep continuing this graph down, you're going to see that each stage has 250, 250, 250, 250, and some pieces might be faster than that, but they cannot proceed because we are doing this in a pipeline manner. So essentially, if you do a pipeline parallelism, your latency is dictated by their slowest the slowest piece in these stages and multiply by it. Remember, when we roll things, right, in a simpler case, let me show you. So here the latency with temporal parallelism was dictated by this. So essentially, if you look at that, that doesn't really change things a lot. So your latency was the length of that stage, right? You cannot go faster than this, right? And then it's pipelined, right? So essentially, you just look at the slowest stage and multiplied it by the depth, how many stages of the pipeline you have. If you have 5, you need to multiply it by 5. So you see, guys, there's no free lunch here. We sacrifice the latency. We spend around 30% extra latency, but we got 4x more throughput from it. And this is trade-off that a lot of designers were willing to take. So this is how pipelining works, right? There's something to sacrifice in the cost of something else. Any questions here? Okay, so really the designs you've seen so far is also pipeline. So no one's going to do their things exactly as I showed you before. All of that is properly pipelined. Stages are separated by a special pipeline register. So this is a little bit more complicated than we draw it. It's always pipeline. So this is to get higher throughput from the chip, because otherwise, as you can see, there is a huge waste when you do things sequentially, right? mostly because a lot of the stages here are independent. So the fundamentally pipelining works because there are stages in the execution of an individual instruction that has nothing to do with each other. When I execute LU on one, I can completely independently execute some read and write from memory that has nothing to do with LU for another instruction. So they don't need to wait for each other. So this is a beauty of pipelining, right? And people who build factories know this for many years, okay? So this is how this data path is gonna look with pipelining. So it would make it even more complicated, even this very simple design. Okay, so far I position everything as we just miraculously get 4x larger throughput. But the problem is that things are not completely independent all the time. So what happens if an instructions need a value that has not been computed? For example, if I had one instruction that does T0 plus equals 2 and another plus T0 plus 3, I cannot say I can do this completely independently, right? Because for me to compute this, I need the output of that. So for me to start certain stages of this guy, I need to know the result of this thing, right? I can't really proceed faster. This problem is called data hazard, right? Which means those data hazards is essentially they add a so-called bubbles in the pipeline. So they make our perfect figures with pipelining way less perfect. And that's essentially hazards related to data. There can be another hazard that's called control hazards that you're very familiar with, that's branches. So we want every time, like if you look here, I want to keep fetching instructions. To me, to do this nice and smooth, I need to know which is the next instruction. Usually next instructions are very obvious. It's the next 4 bytes is the next instructions. And then I just keep going to read and I know ahead of time. But if the current instruction is a branch, by the time it's done, it might bring you to a different place. And then that means that fetch might be wrong. Okay, so as you can see, data hazards and control hazards can break this nice pipelining, right? So this is why architects spend tens of years trying to deal with these data hazards and control hazards, and still to this day, there are a lot of time and billions of dollars spent on dealing with this problem. What are the basic approaches to mitigating the hazards? So one technique for data hazards is called data forwarding, or also called bypassing. So if there are values that are available before they're written back and after the execute stage, you can just forward them. So what does that mean? Is, for example, means that I had registers ready internally in the compute unit. Instead of going and formally write it back to memory or to a different register, if you know that another instructions are waiting for that, do an internal forwarding so that it would take that results immediately from the execution unit, right? So essentially you don't want to wait until memory read and write or write register to finished before consuming something that you know. And that would require some additional wiring in the CPU, but it's definitely worth it because it saves a lot of, otherwise wasted cycles. And sometimes we just have to wait. So for example, if you had a memory instruction that takes 100 cycles, there's nothing else you can really do. And so we're going to inject a lot of no-ops to keep the pipeline stage from doing anything. And that's like a wasted cycles, but that has to be part of the hardware because there's not always that you can overlap things perfectly. Okay. There are other things that can do. So strolls obviously throttle performance. When I do no-op, that makes it functionally correct, but it's wasted a cycle. It's not doing anything in that pipeline stage, right? There are other techniques people do. So the very famous one is branch prediction. So people try to guess where the next branch is going to go and bring you instruction from that location. And in most cases works quite well. The typical branch predictors are 95 to 99% accurate. So it means that even though branches are super frequent, like every 4 or 5 instruction, you have a branch. In 99% cases, I know where this branch is going to go. And this is fundamentally mostly because the code we write is very predictable in terms of branching. Like you had the loops that has like million iterations. I really know that it's going to loop to the same header of the loop again and again. I can predict as well. So if we are correct with branch prediction, we avoid control hazards and we can go next. If we are wrong, then essentially we had to drop the instruction we start to already process because it was a wrong instruction. We didn't jump where we went. So we throw it away and we get like the whole squashed like pipeline stage. So you get like a bubble in the pipeline. It's going to be like a few cycles where don't do anything because you already started to process the instruction that you were hoping that comes next, but it didn't happen. So it means you had to throw away all the intermediate results you have. But the good thing, we are almost no worse off. When I say almost, it means from performance perspective, if I wouldn't speculate, I would have to wait. So I didn't really waste any cycles of doing something useful. But at the same time, I burned some energy. I potentially can bring some data they don't need. So I do some work that's not needed. So I wouldn't be any faster without this technique, but I could spend some energy, right? So Zihan is asking how they predict it. So I didn't see when you type the question. So Zihan, is this about branch predictor? So essentially the way people do, they build special hardware called branch predictors that unfortunately I won't be able to cover in this class. But if you really want to learn more about hardware, you should take like one of the EC classes, EC 352 or 552 that covers branch predictions. Fundamentally what they do by looking at the current instructions, which is a branch because I want to predict branches, they want to guess where you go next. So for example, if I had a loop, right, that iterates a lot, whenever I have this branch, I'm going to see that, and if it's a simple loop that iterates 1 million times and then it exits. So what you can do in your branch predictor for that instruction address, for this program counter PC, you can take the PC, convert it into some smaller form, and then every time you see this PC, you know the branch is going to be taken most of the time. So that's the trivial branch predictor, very easy, right? You know that from that instruction, most of the time, you take the branch and go to the beginning of the loop, right? Because most of the code we write is loops. Things are much more complicated in general because some branches are taken and can flip, that can be, say, you can have something like if I mod 2, and then it can be 0, 1, and can flip-flop. Those can be also detected. Essentially, people build a hardware that can guess the patterns of jumping, and they make predictions based on this information. I know it's very simplified here. In EC, they're going to have the full lecture on branch predictions, right? 2 or 3 hours on that, on how it's done. And people spend 40, 50 years on working on this topic. So it's not like an easy thing, but fundamentally the reason why things are predictable and possible to predict because the code we write is not random. We write it in a certain way using operations like loops, and those branches are very predictable. Zihan, did I answer your question? Okay. So the summary here is the pipelining offers a trade-off. It added additional hardware that increases throughput, sometimes dramatically, for somewhat of an increase in latency and complexity of the design. This trade-off universally accepted, and even architectures that go for spatial parallelism, like GPUs, for example, there are a lot of other forms of parallelism, usually also had some form of pipelining. Where the difference happens is that, for example, in CPU, the pipelining is one of the major ways to get parallelism. And then your pipeline is very deep and detailed, like modern Intel CPUs might have 20 stages in the pipeline. I show you 5 stages, but this is more like CPU that were built 30 years ago, right? On the other end, while we don't know the exact details of NVIDIA and AMD GPUs because it's proprietary, we can speculate based on some information. They're very simple pipelines. So there are 5, 6 stages. So simple pipelining is such a powerful idea and gives so much benefit. So even spatial architectures still use pipelining. It's a very powerful You know, it's one of a few things that you always use in different contexts in hardware, pipelining, similar to speculation. This is ideas you're going to see again and again, and prediction. So everything around hardware is usually around those topics. Okay. Okay. So I think that's everything I have for today. Any questions, guys? Okay, if there is no question, then thanks everyone. Please prepare for the quiz as usual. Yeah, Zihan, question, go ahead. The last page of recursion convention. Okay, what exactly there? Oh, the recursion convention, what's the benefit of it? The benefit of it is if you can't assume that the registers, say T1, T2, T3, T15, are not used by someone else, then the problem is then you would have, before using them, you would have to store them somewhere on the stack, use them, and then restore the value. So Zihan, does it answer your question? So essentially the benefit is that you don't need to write a lot of code for, like, say if I need 3 registers to do my compute, if I don't have temporary working registers, I would have to take the current value of each register, put it on the stack, play with it, and then read the value back on the stack. So you, like, just to use 3 registers, you would need to use like 6 instructions, right, at least. With this convention, you can just directly go use them without any extra instructions. And remember that stack manipulation might be actually not accesses to register, they will be accesses to memory. They are very costly. So Jonathan, your question was, is that how we fix the nested function calls? Yes, the nested function calls is essentially no different from recursion fundamentally, right? You just follow the same principles, right? You might not necessarily call the same function, but it's essentially you can pull everything on the stack, use the same philosophy, and everything is properly recovered. Okay. Okay, so then the question from Sam, does CPU parallelism for graphics require multiple cores? So I wouldn't call it CPU parallelism, let's call it pipeline parallelism. There's pipeline parallelism and essentially spatial parallelism. So multi-cores these days are used in both CPUs and GPUs because that form of parallelism is useful in many different contexts, right? In the GPU context, it's just the trade-off is somewhat different. They try to hide the latency way more aggressively for memory. So the number of cores for the GPUs are close to 100, while so SM cores, that's how they called, NVIDIA calls them, simultaneous multiprocessor. And in CPUs, the number of cores that tend to be smaller. Like the typical CPUs you use have 4-8 cores, but there are some huge CPUs with a lot of cores as well, like 40 cores and more. Okay. So essentially, this is like, it's not CPU or GPU parallelism. Essentially, both designs try to fundamentally exploit 2 types of different parallelism. One sequential, right? So one is pipeline for a single thread, and another one for multiple threads, spatial. Sam, I hope I answered your questions. It's in general a question that would require looking into more advanced version of computer architecture classes, which we offer, but not for second year, more like for third, fourth year students. That's where we cover those things. Jonathan, you're asking, and what is the difference between T registers and S registers, so putting them return address to the stack? So fundamentally, they're not different. It's just a convention. So people even put different names for them, so you don't get confused. So when you write your own code manually, like compiler won't get confused, they know what to do. But you as a human can get confused. If somebody would tell us register from 1 to 7 and register 15 and 13 are safe, and register 12, 18, and 19 are not safe, that would confuse you. Now they come up with a convention name whether T registers are safe to use inside the function, S registers needs to be saved, right? This way, you know, the name of the register already tells you what is safe versus not safe, right? Okay, and yeah, so there, and return address, you always need to put to the stack, so if you want to come back, yeah. Okay, I hope I answer all the questions, guys. So does this week's quiz cover the lecture today? As usual, we'll try to mostly be on the previous week, but somewhat on this week, right? Like, and also remember, we take into account everything. For example, tutorial covered recursion a little bit, so you're supposed to be familiar with that, right? But again, it's not going to be heavy on it. And remember, guys, like, I'm going to keep asking questions about caches until majority of you is going to do it right. So be ready for caching questions. They're going to happen until you do it right. So Eric is asking, can you explain the latency difference with the 5x25 again? So, okay. So this place, right, Eric, you want to learn. So essentially, I'll go without 5, I go instead here. I think this is the easiest. So if you look here, if I had just 2 stages, I only had a roll and bake, right? When I'm going to do my pipelining, you're going to see that my throughput is going to be fundamentally bottlenecked by this guy, right? Because these things, you can put it here, there, doesn't matter. Each of these is sequential. So essentially, if I try to get the latency in this approach where there's only a single thread, I'm always limited by the slowest step, right, in my pipelining. So essentially, because each of that cannot be overlapped with anything, and they are sequential with respect to each other. I cannot bake second tray until I finish the first one, so they go one by one. So in this case, you see, so this addition, little addition, doesn't really change the results a lot. So really the latency is a multiple of this thing, right? So then if you had the more stages you have, the more additional latency you get. So essentially, if you had a fetch like that, everything has to be aligned with that stage, right? Because that's the way you build pipeline. There's going to be some bubbles here. So the fact that some stage is a little bit faster doesn't speed up things anymore. So yeah, the bottom, like if you look at these things, fetch instruction, or memory read, they had the longest latency. So the overall latency is going to be dominated by these guys because they not nicely overlap with these things. So essentially, at the end of the day, if you're going to look at the latency, your latency is a fixed, right, stage. So if you look here, it's like this instruction is going to do 250, another 250 because it has to align with fetch, right? Another 250 because it needs to align with this fetch. And then another 250 because it has to align with the fourth fetch, right? And then another fetch here. So essentially, it's only going to end here, which is after 5 fetches, right? So essentially, it has to be aligned for each of this guy, right? So if I'm going to go fetch, 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 and that's the longest latency, this guy has to align with that, so it's not going to finish until here. So because of that, it's going to be, somewhere here. And if you look, it's going to be here, right? That's where I finish. But if we are doing the instruction at the same time, the problem is in the pipeline parallels, there's only one bakery. There is only one thread to compute. So I cannot do 2 instructions at the same time because it's fundamentally sequential, right? So I cannot jump over that. So like you can think about, I only had one thing to bake or one thing to execute, right? So I can't really fetch 2 things at the same time. If I would happen to be able to do it, that would be spatial parallelism. I would do 2 fetches at the same time or 2 executions at the same time. It's 2 different forms of parallelism fundamentally. Eric, does it answer your question? So yes, I would save time if I could do it, but I not always can do it because I might not have the ability to fetch multiple things in parallel. Okay. Yes, we are in pipeline parallelism. We assume that we can only do one instruction at a time, right? One stage of an instruction at a time. So I can parallelize different pieces of that process of the instruction. I can bake and roll at the same time because it's independent, but I cannot bake three things at the same time. But that's possible in spatial. Okay, thanks everyone. Bye.